Hello everyone. The differential equations that we are going to learn in this video are called linear differential equations. So let's begin with the general form of such equations. A first order first degree differential equation is said to be a linear differential equation if it looks like this: dy by dx plus py equal to q. That means the derivative of y with respect to x plus p times the dependent variable is equal to q, where p and q are functions of the independent variable x only. So whenever you come across a differential equation which looks like this, the derivative plus a function of the independent variable times the dependent variable is equal to another function of the independent variable, such equations are called linear differential equations. And there's a set procedure for solving such differential equations. That's through finding something called an integrating factor. Whenever we see such a differential equation, we start by finding out the integrating factor of such a differential equation, which is abbreviated as IEF. It's given by e to the power integral of whatever function is appearing with the dependent variable y here, that needs to be integrated with respect to x, and it is to be raised to the power e. So this expression which you obtain after doing e to power integral p dx is what is known as an integrating factor, and this comes under a very special category of non-exact differential equations which can be reduced to exact by finding this integrating factor. So that's a different theory altogether. Why this procedure is followed comes under something which we are going to discuss in the subsequent videos when we talk about non-exact differential equations and finding ways of making them exact. But for now, let us understand that a differential equation which looks like this can be easily integrated. Its solution can be obtained just by finding e to the power integral p dx, and the solution is given by the dependent variable times what you obtain above as IEF in this step is equal to the integral of the right hand side function q times the integrating factor. So that's the end of the story. Once you see that it's a linear differential equation, just straight away find out e to the power integral p dx, and the solution can be written as the dependent variable y times the integrating factor is equal to the integral of right hand side times integrating factor. Why this is happening is a different theory altogether, which we are going to discuss in another video. But for now, let me demonstrate this technique through some examples. Let's look at this example to begin with. Suppose the differential equation given to us is dy by dx plus 4x upon x square plus 1 y is equal to x upon x square plus 1. So let's look at this differential equation. If we are asked to solve this differential equation, then comparing it with the standard format of a linear differential equation, we can see that dy by dx plus p, here you should have a function of the independent variable only. So you can see that this is serving as p if you compare it with the standard form, and the right hand side function should also be a function of the independent variable only, which we are calling as q in this. So the procedure says that you just take p, integrate it and raise it to the power e. So what will be e to power integral p dx? It will be e to power integral of 4x upon x square plus 1 with respect to x. You need to integrate it. Now how do we integrate it? We can just put x square plus 1 as t, 2x plus dx turns out to be dt. So we can see that this expression, this integral which we need to calculate, is actually 2 times dt upon t, which can be written as 2 log t, but t was x square plus 1. So our integrating factor, integral which is involved in the integrating factor, takes this shape. So I can put the value, this integral has got the value 2 log x square plus 1. And we know that log and e are inverses of each other, so I can use the property of log to take this constant here in the power of log to write it like this, and then since e and log are inverses of each other, my integrating factor boils down to this expression. So this is what is obtained after doing e to power integral p dx, and the solution, as I told you in the beginning, that the solution is very easy. It's a one-liner. Why does it happen to be this is another theory which we are going to discuss when I do non-exact differential equations in the subsequent videos. I'm going to tell you why this serves as an integrating factor, but for now you can just remember the technique. The solution is dependent variable y times the integrating factor which has been obtained in the above step is equal to the integral of right hand side. Let's see what is q. Q is x upon x square plus 1. So it's x upon x square plus 1 into the integrating factor. You can see that this cancels with this and we are left with the integral of x cube plus x, which is easy to integrate. Powers are very easy to integrate. It's x4 by 4 plus x square by 2, and of course you do have a constant of integration attached to it in the end. So the solution looks like y into x square plus 1 whole square is equal to x4 by 4 plus x square by 2 plus c. So that's the general solution of this differential equation that we began with. It was falling in the linear category, so we adopted the technique of solving linear equations by finding integrating factors, and that's how the solution looks like. Now there's something that I would want to comment on before I end this video. So see, when you have dy by dx plus py equal to q, please do not read it in this format. Read it as the derivative plus function of the independent variable times the dependent variable is equal to another function of the independent variable. Because sometimes what happens is that the dependent variable, you are taking it to be y. That's the normal convention. We take y as a function of x. But sometimes the equation is not linear when you talk about dy by dx, but it suits you more to take dx by dy. That means you take x as dependent in that setting and y as independent. So your linear differential equation can also look like dx by dy, because x is playing the role of the dependent variable now. So here you can have an equation which looks like dx by dy plus px, because x is dependent now, is equal to q, where p and q now this time will be functions of y. So this is also a linear differential equation. It's just that the roles of x and y have been reversed, and the procedure will still be the same. You will find out the integrating factor. It will be the integral of e to the power integral of p dy this time, because y is playing the role of the independent variable, and your solution will be given by x, which happens to be the dependent variable, into integrating factor is equal to the right hand side, which is q, into the integrating factor. So the roles of x and y are going to get reversed if it's linear in x and y instead of y and x. So let me illustrate that through one example. Let's take dy by dx equal to, let's say, 1 upon x plus y. Now this equation we know how to solve using a technique which we had discussed in one of the videos earlier when we were talking about reducible to separable category. We can put x plus y as t and then simplify it in terms of t and x. It becomes reducible in terms of t and x. But let's see, when you have x plus y in the denominator, you cannot separate. But if you take dx by dy, then reciprocating this expression makes x plus y go into the numerator. So if you compare it with the linear form now, it's dx by dy. X is the dependent variable. Dx by dy plus px. So what will come here? Minus 1x equal to a function of y. So you can see that this is my p now. This is my q in the linear format if I talk about dx by dy instead of dy by dx. So my integrating factor would be e to the power integral of minus 1 dy. That's equal to e to power minus y. So the solution, instead of doing it by reducing it to separable, I can look at it the linear way and solve it using the linear method of solving differential equations. So my integrating factor is e to power minus y, and hence my solution will be x, the dependent variable, into the integrating factor is equal to the right hand side into the integrating factor dy. Now this is a very easy integral if we know by parts. It's a one-liner. First function integral second minus integral derivative of first integral second. So that's what it looks like. And one more step if I do, I can rewrite it as e to power minus y upon minus 1, and then here is going to be my constant of integration. And so my solution looks like x into e to power minus y is minus y e to power minus y minus e to power minus y plus the constant of integration. And see, we have e to power minus y coming in 3 terms, so let's multiply throughout by e to power y to make it look better. So that's how the solution looks like, or I can rewrite it to finally present my solution in this form. So this example serves as an illustration of using the linear technique when the x and y roles have been reversed. So please keep in mind that linear differential equations are those differential equations which have this format, that the derivative plus, so y, when you talk about derivative, there will be a dependent variable which happens to be y in dy by dx, and x which is the independent variable. So derivative plus a function of the independent variable times the dependent variable is equal to another function of the independent variable. That's the class which can be solved using this technique of finding integrating factors and then finding the solution via this step. So that's all on linear differential equations. In the next video, I'm going to tell you about differential equations which are not linear but they can be reduced to linear, and such equations are called Bernoulli equations. But for now, let's end the video here. Thank you so much for watching, everyone.